Hello, Professor. This is Group 9. Our project is focusing on a pricing strategy for cryptocurrency trading platform. Next.
Oh.
And next. The cryptocurrency market is a fast-growing and highly valued market. The Singapore government values the opportunities and takes a caution but supportive stance towards the cryptocurrency market. In this background, we focus on a cryptocurrency trading platform. One kind of cryptocurrency trading platform is that the platform deals directly with the customer rather than acting as an agent. They make profit through buying at low prices and selling at high prices. To trade with such platforms, customers should firstly choose tokens that they want to exchange, and then the platform will give their quotations. Given the quotation, customer can choose to accept the quotation and complete this transaction or reject the quotation. Next. And our work is leveraging machine learning methods to help such platform optimize its quotation strategies. That is, giving a price which customer will accept as high as possible. The core of our approach is the application of a choice model. One important concept of choice model is the trader profile, a profile depicting a customer's historical trading behaviors. We use clustering methods to do profiling. And then, based on trader profile, quotation given by platform, as well as other features, we build some machine learning models to predict the acceptance of each quotation. My teammate will introduce the details of our methods and our models.
Firstly, I will provide an overview of the clustering analysis conducted to develop trader profiles based on historical trading behavior. The goal of this analysis was to gain insights into traders' risk tolerance, trading frequency, preferred cryptocurrencies, and reactions to market fluctuations. To begin, we utilize unsupervised machine learning techniques, specifically clustering, as we do not have predefined criteria or label samples for categorizing customers. The clustering process involved two models, Gaussian mixture model and the K-means. Before the clustering, we selected relative behavior and market features, and then excluded 5 columns due to correlations of over 0.8 with other columns. Next page, please. Let's focus on the Gaussian mixture model. GMM is a statistical model that represents a dataset as a mixture of several Gaussian distributions or clusters. The algorithm works through an iterative process employing the exploitation maximization algorithm. In the E step, the algorithm calculates the probability based on current parameter estimates. And in the M step, it updates the parameter estimates with the results in the E step to get optimal parameters. Next page, please. Choosing the appropriate number of components is crucial. We use information criteria such as AIC and BIC to determine the optimal number. Lower values of AIC or BIC indicate a better trade-off between fit and complexity. In our case, the results indicated that 5 components were the best choice for clustering in GMM. Cluster A may represent common individual investors, B potentially indicates speculators, C and D may represent larger and small to medium-sized institutional investors respectively, and cluster E might indicate high-frequency quant investors. For K-means, let's pass to Kelly for the introduction.
K-means is another popular unsupervised machine learning algorithm to categorize unlabeled data. It separates data into K-distinct and non-overlapping clusters. We have opted to use this method because of its simplicity, efficiency, and easy implementations. And the goal of K-means is to minimize within cluster variance by using the sum of square Euclidean distance. And the steps to implementing K-means is first to define the number of clusters, and then to initialize centroids, and then we assign data points to near centroids based on the distance, and then we update the cent choice based on the data points in the cluster. Lastly, we iterate the step 3 and 4 until the cent choice no longer change significantly. Next, we'll take a look how we use our k-mean clustering in our case. So in k-means, we use the elbow method to find the optimum number of clusters. So in this case, it is 4. And then just like GMM model, we have identified a few clusters, and in this method of using k-means, we have identified a few the clusters. So the clusters are categorized in the following. So some of them will have low cross entropy and quote times, and some of them will have highest sell percentage of trading directions. And now let's pass on to Mia and Ihan to talk about classifications.
So where clustering is a physical process of selecting samples with similar features, classification is to divide samples under known categories. Here lists 5 classification models in our analysis. On the right-hand side are the model evaluation indicators. We choose a model with best performance, mostly based on accuracy and precision. We might also take recall and F1 score into consideration, since there are 208,100 data labeled as 0 and only 2,000 labeled with 1. Thus, we use SMOT to deal with the unbalanced data. We also remove the means and scales for each feature's variance to unit with the standard scaler. So here listed the classification result with GMM in 5 clusters. As we can see, the random forest has the highest accuracy as 98%, where XGBoost followed at 97%. However, the precision rate of XGBoost is higher, which means that out of 100 times that the price rose indeed, the number the model successfully predicted was 23.67. Thus, we choose the XGBoost as final model. Also, XGBoost provides a built-in feature importance score for each feature in the dataset. Thus, we can improve our model by drop some less important features. On the right side, there are the 4 top mean features. So next, Ihan will introduce us the classification with k-means clustering.
Okay, thanks. Next, I'll introduce the model performance based on k-means clustering. Logistic regression has low accuracy compared to other models. Its low precision indicates the model generates a large number of false positives. Despite high accuracy, the random forest has low precision and recall. It may generate false positives. XGBoost has balanced performance with reasonably high metric figures, meaning that it performs better at capturing true positives compared to logistic regression and random forest. Then SVM has a reasonably high recall, capturing a good number of true positives, but the precision is low. Finally, neural network achieves moderate accuracy, but low precision and recall, which means that it may not be capturing all true positives and may generate a higher number of false positives. Looking ahead, since Since our main issue faced was the unbalanced dataset, we've identified key areas for improvement. Firstly, it can be seen that although we have high accuracy in general, but precision and recall are relatively low. We understand that accuracy alone doesn't fully capture model performance, especially with unbalanced datasets. In fact, our models may overpredict the majority class, leading to diminished performance for the minority class. As for future study, we should consider data balancing methods beyond SMOT, such as oversampling with A to C, undersampling with near miss, or a combination of these approaches. Secondly, adjusting model parameters, like modifying the class weight in random forest and XGBoost, or use a weighted cross-entropy loss function in neural networks. Lastly, let's not overlook other suitable algorithms for unbalanced datasets. For example, we can apply cost-sensitive learning by adjusting the error penalty term in SVM. That's the end of our presentation. Thank you all.